Welcome back to our physical science unit over energy. If you've been following along with us, we've been going through the different forms of energy. We've talked about several so far, and we are on lesson 8, which is over sound energy. So this lesson is just going to be a brief overview of sound as it relates to energy. But you do need to know that sound is a form of energy, and it's produced and transmitted by vibrating matter. So if you'll remember in our previous lesson over mechanical waves, there's 2 types of mechanical waves. We have transverse waves, and then we have longitudinal or compressional waves. They're interchangeable. And these compressional waves or an example of these compressional waves are sound waves. So sound is carried to our ears through vibrating air molecules. So the air would be considered the medium through which sound travels. So if you can hear my voice right now, it's because sound energy is being transmitted from my mouth to your ears. And what's happening is the energy is creating vibrating air molecules that are vibrating and touching another air molecule that causes a vibration, which touches another air molecule, which causes a vibration, all the way to the receptor, which would be your ears. So our ears take in these sound waves and turn them into signals that then go to our brain, and that's how we register sound. Now, again, just mentioned, sound has to have a medium in order to travel. So a few lessons back, I asked you if sound traveled in space, and I said we'll come back and revisit this question. Well, we're here now. So the answer, hopefully you said in the previous lesson, is no, sound cannot travel in the vastness of space. And if you're asking yourself why, the answer is because there are no air molecules in the vastness of space. It's what we call a vacuum. And since sound needs these air molecules to travel, there is no sound in space. So here is a picture of these compressional waves. You can see the sound vibrates matter or air molecules, and the energy of the sound travels from the source to the receptor. Again, sound is known as a compressional, otherwise known as a longitudinal wave. So we hear sound, which usually travels through air, but sound can travel through other mediums as well, and it travels different depending on the medium. So sound can travel faster in some mediums than others. And I want you to try to answer this question. Do you think that sound travels faster through solids, liquids, or gases? Now, typically sound is going to travel faster through solids, and the reason has to do with the molecules. So when we get to our matter unit, we're going to learn that the molecules of a solid are tightly packed. They're right up next to each other. So what tends to happen in a solid is when one of those molecules vibrate, it creates a quick chain reaction through the other molecules because they're touching one another. Liquid molecules are a little more spread apart, so it takes a little while longer for that energy or that vibration to get from one molecule to another. So sound tends to travel slower in liquids as opposed to solids. And even slower in gases, because we know the molecules of a gas are spread apart, and so it takes a little while longer for those molecules to transmit those vibrations. If you look at this chart, this is just showing the speed of sound in different mediums. And you can see aluminum is the medium through which sound travels the fastest in. And so sound does travel faster in metal materials, typically. Now, we can measure sound in terms of how high or low a sound is. So we use the word pitch to describe the frequency of a sound wave. So your high-pitched sounds are going to be high-frequency waves, which remember is also lower or shorter wavelength. Then your low-pitched sounds are very low-frequency waves. These are going to have a longer wavelength. If you'll look here, number 1 says sound wave A has, and you choose a higher, a lower, or the same frequency as sound wave B. So let me go back. Sound wave A, would you say that this has a higher, a lower, or the same frequency as sound wave B? Hopefully you chose higher frequency. So sound wave A has a higher frequency than sound wave B. All right, if you'll look at question number 2, sound wave A has a higher, lower, or same amplitude as sound wave B. Remember, amplitude is the loudness of a sound, and it's going to be categorized by very tall waves. So it's hard to tell here without like a measurement. It looks as if A might have the same amplitude as B, even though the frequency is higher than A, the wavelength shorter in A. I think if we were to actually measure this, we might find that it has the same amplitude. All right, let's look here at these comparative waves. If you'll look at the very first question, it says sound wave A has higher, lower, or same amplitude as sound wave B. So sound wave A, does it have a higher, a lower, or the same amplitude as sound wave B? Hopefully you said higher, and this is obvious. And the last one, it was kind of hard to tell, but this one's obvious. Sound wave A is going to have a much higher amplitude. So this sound is going to be a lot louder. Sound A is going to be a lot louder than sound B. Now at the bottom it says sound wave B is louder or more quiet than sound wave A, and we just answered that. So B is going to be a much quieter sound than A. All right, so that brings us to the Doppler effect, which is a phenomena that happens with sound waves. So if you've ever been just standing in your yard when a police siren goes by or ambulance goes by, you may notice that the sound gets louder and louder and louder and louder as it comes towards you, and then it kind of fades away as it moves away from you. This is called the Doppler effect. So it's an observed change in the frequency of a wave when either the source is moving or the observer is moving. So when the siren of an ambulance drives by, the siren changes from high pitch as it gets towards you, and then as it moves away from you, the pitch decreases. Now, why is that? And the answer is the pitch of a sound is basically how high or low it is. And this is determined by the frequency at which the sound wave strikes our eardrum. So we're the observer, we hear the sound, and the frequency at which the sound wave strikes our eardrum is going to have to do with what we experience with regards to the Doppler effect. So when an ambulance heads towards you and it has its sirens on, the sound waves are actually going to compress. So when you have a sound source that's moving, the sound waves kind of bunch up in front of the sound, and that increases frequency. Well, when the frequency increases, the pitch increases, and that's why it seems to get louder and louder and louder as it moves towards you. Now, the opposite is true as well. When that sound moves away from you, the sound waves spread out. That decreases the frequency, which decreases the pitch, which is why it sounds like it's moving away, like it sort of dissipates as it moves away from you. So here's a visual representation of the Doppler effect. You can see the sound source. You can see the little guy on the right side. The sound waves are moving towards the observer. So the frequency is much higher here. Those sound waves are compressed. So he's going to hear a louder, higher frequency sound or higher pitch sound. Now the guy on the left, since the sound source is moving away from him, those sound waves are decompressing. They're spreading out, longer wavelength, lower frequency. So this is why he's going to hear a lower pitch sound. Now, look at this question. What would happen if a an object were to outrun its sound waves. So we saw in this picture where sounds kind of bunch up in front of an object when an object is making a sound and the object is also in motion. But what if that object were to move faster than the sound waves could keep up? Well, if you answered a sonic boom, you're correct. So when an object outruns its sound waves, you hear a loud noise, and this is known as a sonic boom. All right, so that ends our lesson over sound waves and the Doppler effect. And in our next lesson, we're going to learn about light, energy, and ways that we see and how we see color.